All right, on Friday we talked about t-squared, or taking a t-test, hypothesis testing for the t-test. It is very similar to the z-test. You find a t-test value the same way you find a z-test value. Nothing is too much change. The only thing that changes is how you find your critical values. Dealing with your critical values and looking at your t-table, you have to deal with the degree of freedom. Looking at the degree of freedom, you find your critical values with your degree of freedom. Questions you have about any of the problems with respect to a t-test? I'm sure you all work very diligently, making sure you got your homework done over the weekend. I ain't no dummy. I know whatever didn't get done on Friday afternoon in this classroom probably didn't get accomplished then after that point. Today we're going to talk about hypothesis testing with the chi-squared for standard deviation and variance. Tomorrow we have an in-class assignment and a combination of all these things put together. We're just going to have a review day. Tomorrow we'll have a review day over all the chi-squareds, or all the hypothesis testing stuff. Okay, trying to get everything accomplished by the time we get out of here. My goal, once again, is to have our final taken before we leave for Christmas break. So we will push ourselves to get ourselves to the point where we have an opportunity to take the final. Okay, if we take a look at testing for your variance, it's not going to change. Things aren't going to change much when testing for the variance, hypothesis testing. We're going to state the null and alternate hypothesis. We're identify as going to be a one-tail or two-tail test. Our degree of freedom is your sample size minus 1. That all these things are not changing at all. We're going to find critical values from our chi-squared table. So on the back of the t-table, on the back of your t-table, we have our chi-squared table that we've utilized already. To find our critical values, and it is fine to write this on your chi-squared table. If this is a one-tail, left-tail test, you're going to use 1 minus alpha. So on your chi-squared table, it's okay to write, if it's a left-tail test, I'm going to use 1 minus alpha. And if it's a right tail test, I'm just going to use alpha. And if it's a two-tail test, I'm going to use 1 minus alpha divided by 2 and alpha divided by 2. And once again, please do write this on your chi-squared table. And once again, it's going to be the exact same idea. Now, the chi-squared bell-shaped curve is not the same as just a normal distribution. Okay, but I still utilize my normal distribution. You're going to find your critical values, whatever your critical values are. If it's a two-tailed test, I'm going to find my critical values here. Okay, and then we're going to calculate a test value. Okay, our test value is, once again, what we used. I guess we didn't use this as much. But when we're dealing with a test value here, we got our degree of freedom, our variance is what we use for a confidence interval. Our variance, sample variance, divided by our sample standard deviation. I'm sorry, population variance. And once again, it is important that you read the problem and determine what is given to you. If I give you the standard deviation, you're going to have to square this value. If you're given in the problem the variances, you're not going to have to square the values because your variance is already your value squared. And once again, if your value is in the critical region, you're rejecting the null hypothesis. We're going to have non-critical. And when we're in our tails, we have critical. We take a look at a problem. A Weather Service claims its standard deviation of the number of fatalities per year from tornadoes is more than 25. Random sample of number of deaths is 28 in the 28 years, has a standard deviation of 31 fatalities. Alpha value 0.10 is enough evidence to reject the null or reject the hypothesis. So we start as we've done already. Your null and your alternate hypothesis. What he is hoping, not what he's hoping, but what he is claiming. Obviously, we don't want to have fatalities during tornadoes, so the hope of a fatality is something that you don't want. But what he is claiming in his statement is that it's going to be more than 25. Okay, so what we're looking at here is we're looking at the standard deviation. So our standard deviation, which is sigma, is more than 25. We're not talking about the mean. Okay, if we're talking about the mean, we would have the value of mu there, or the symbolization of mu. But we're talking about the standard deviation. And once again, with the null hypothesis, it's the opposite. And we have equality always going with the null hypothesis. So we have sigma is less than or equal to 25. So if we take a look here, we have sigma is 25. We have taken a sample of 28 years. And in the 28 years, the sample standard deviation is a value of 31. We have an alpha value of 0.10. We have a degree of freedom of 27. So if we look at our critical values, once again, I know it's not a normal bell-shaped curve, I get it. If you look at your chi-squared table at the bottom, it's looked like a skewed values to the right. The Sally with the camel's hump is on the left with the standard deviation, the chi-squared, which is fine. Do we have a left tail test or do we have a right tail test? Jenna, what do we have, left or right? The right tail test, because our alternate hypothesis is greater than, so we have our critical value going to go to the right. We have a degree of freedom of 27. We have a right tail test. So if we take a look at a right tail test, we're going to use an alpha value for our critical value. So we're going to use this and our degree of freedom of 27. So we go to our chi-squared table. We go down to the degree of freedom of 27. We take it over an alpha value of 0.10. Lucas, what do you get? 36.741. So we go to our chi-squared test, which is, we have n minus 1 s squared divided by sigma squared. Okay, that is our variance. We are given standard deviations, so we're going to have to square those values. So we have 27, s squared is 31, squared divided by sigma squared, which is 25 squared. Once again, if the variance was given to you, then you would not be squaring those values. Since the standard deviation was given to you, we are squaring those values. Justin, what did it come down to? 41 point what? 41.52? Yes, no, maybe so. Okay, now with the chi-squared, this is just a number line starting at a value of 0 here. Okay, I don't have a plus minus here with my chi-squared, so I get thrown out into here, which is a critical region. We have non-critical here, so we can reject the null hypothesis. Of the standard deviation being 25. And we can conclude that it is more than 25. The doctor says standard deviation length stay to patients involved in a crash which a vehicle struck a tree is 6.14 days. Random sample 20 lengths of stay of patients involved in the type of study or type of crash has standard deviation of 6.5 days, alpha value 0.01. Okay, what he is saying, let's see, it is 6.14. Okay, so what he is stating that the doctor says the standard deviation for the stay of patients involved in a crash in which it strikes a tree is 6.14 days. Okay, so we're just saying that we have this exact value. So we have our null alternate hypothesis. When we're stating that it is this value, we're not saying it's more than, it's less than, it is this value. Ethan Stutz, what are we utilizing here for our null and alternate hypothesis? We're saying it is this value. Equal to. So we have equal to and not equal to. Once again, equality will always go with the null hypothesis. So we're saying sigma is 6.14. We have a sample of 20. We have the sample standard deviation of 6.5. And we have an alpha value of 0.05. Degree of freedom would turn into 19. No, one tail or two tail? Two tail. So if we have two tail, to find our critical value, we have a degree of freedom of 19. Two tail, we use alpha divided by 2 and 1 minus alpha divided by 2. So we have to take our alpha divided by 2, 0.05 divided by 2, so we got 0.025, bless you. 0.025, and then 1 minus that. So we should get what, 0.975? Okay, good. Your table, find your critical values. What's your two critical values? For the degree of freedom of 19. Once you find your critical values, calculate a chi-squared test value. Okay, with our alpha values, we have alpha divided by 2.025.975. Our two critical values, 8.907, 32.852. Your two critical values, I hope. Okay, our chi-squared, we have 19, our degree of freedom, 6.5 squared divided by 6.14 squared. So when you find our chi-squared test, Grayson, what do you come up with?
21.29.
21.29, good with that. So we lie in between these two values, so this is non-critical, critical, critical. So we fail to reject the null hypothesis. So the claim of 6.14 is a feasible standard deviation. That is a feasible standard deviation that the doctor was claiming. Same type of idea, it's just a different way of how we calculate our test value. Okay, it's just a different way of how to calculate the test value here. Question you have about chi-squared? You have 15 minutes here. Should be able to get through a few of these. Yes, time is yours.